Section 1-3 is titled the definite integral. If you recall, one of the 4 topics of calculus is on definite integrals. The objective is, given a function, estimate the definite integral by counting squares. So there's 2 things we need to figure out here. What, first of all, is a definite integral, and then secondly, described as counting squares technique. So let's start with the definite integral. And we'll give ourselves a simple definition here to start out with. In fact, to simplify this even further, I could simply say that it's just area. But we need a little bit more information than that. So I have it's the signed area between the function and the x-axis. And I say signed area in quotes like that because area by definition is always positive. And we'll find that definite integrals can be positive or negative, depending on the region, depending on the function, depending on the interval that we're talking about. So it's the signed area between the function and the x-axis. All right, with that, knowing that it's area, we just need to remember what exactly this counting squares technique is, and I say remembering it because if you go back to elementary school, when you first were introduced to this idea of finding area or calculating area, you were probably given some nice geometric figure, probably a square or a rectangle to start off with, and you were given some grid or graph paper to put that geometric figure on, and then count up how many squares were inside of that geometric figure. That's very similar to the technique that we're going to use here. I say similar because when you did it before, there was one step that you probably left out in that process that we need to consider here. But also, you had a nice geometric figure to work with. That's not the case here with these types of problems because of the fact that it's the area between a function and your x-axis. So it's not going to be a nice geometric shape. Let's talk about the technique. It's really a 4-step process here. First step is to count the number of whole squares. You have to get yourself a graph of this thing so you can see the function as well as the x-axis, and then go through and count up how many whole squares are in that region that you're considering. Once you have done that, the curve is obviously going to cut through some of those squares. So we'll refer to those as the partial squares. So go through and count up the number of partial squares, and we're going to try to do that to the nearest 10th. Now, as you're doing that, you might look at one square and say, that looks like that's 0.2. Somebody else might look at it and say, no, it looks like it's 0.3. Somebody else might even look at it and say, no, it's 0.1. You don't have to worry about that. Pick one of those and move on. It's an approximation technique, and any one of those is close. If you think it's 0.2 and somebody else says it's 0.8, there's a big difference there. Somebody's wrong. Figure out which one's right and use that area. Move on to the next one. This next step is the one that I said in the elementary technique you didn't have to worry about. But here we do have to make sure that we do this, and it's probably the one step that's most forgotten here, in fact, is to find the area of one square. Going back to your elementary example there, when you laid it on that grid, the area of each one of those squares that you were counting up was actually an area of 1. So it turns out that the number of squares is exactly equal to the area of that geometric figure. That works only if the area of each square is 1. That's not going to be the case for the problems that we're going to consider. There might be some where the area is 1, but by far the majority are going to end up having areas that are not equal to 1. And once we have those pieces of information with some multiplication, of course, we can then find the definite integral, or a good approximation for the definite integral, by multiplying. Multiply the total number of squares, both your whole squares and your partial squares, by the area of one square. And that should give us a very good approximation, actually, of the definite integral. Now, there are some other techniques that will definitely give us better approximations, but you'll be surprised, I think, when you start working on some of these problems, how close you actually are to the exact area. All right, let's start with an example here, and this example here is on page 14 in your book. They give you a graph there at the bottom of that page, and they, in the very last paragraph, describe what that graph is modeling. It says, suppose you start driving your car. Velocity increases for a while, and then levels off. The figure there shows the velocity increasing from 0, then approaching and leveling off at 60 feet per second. All right, so let me just kind of sketch what this graph looks like here. You increase pretty quickly to 60 feet per second and then levels off. So this right here is 60 feet per second, we'll say. So this is our velocity in feet per second. It's our dependent variable, our y-axis. And this is our time down here, and that's in seconds. And they've also got a couple of values marked here along our x-axis, so I'll mark those as well. Here's 30, excuse me, that's 0, here's 30, and 70 is somewhere about here, it looks like, and they also have 100 marked. Okay? So the question here in this example is, can we determine how far we've traveled from this velocity function? So if we recall some work that we've done in physics, or in previous math classes for that matter, we should recall that velocity times time will give you actually your displacement. In this case, though, since our velocity is positive, it's also going to give us the distance. So I have those two numbers I could actually punch in here and actually find the displacement then. Let's consider the interval from 70 to 100 seconds. That is, let's consider this 30-second interval right here. That's 30 seconds from 70 to 100. So for that 30-second interval, I know how much time has passed, 30 seconds. And I also know from the graph that I was traveling at 60 feet per second for that entire interval. So I also know the rate that I was traveling at, or the velocity. So I can plug those two things in. My velocity is 60 feet per second. My time is 30 seconds. And so I can calculate the displacement by multiplying those two. So 60 times 30 is 1,800. Notice, by the way, that these seconds are going to cancel out here and leave us with just 1,800 feet. Now, if you consider what we've actually found here, it's an interesting connection here to the definite integral when we look at the graph. That the 30 seconds, as you can see I've marked on that x-axis there, is actually indicating the horizontal distance that we traveled. Or excuse me, it's marking that distance from 70 to 100 seconds. And if I mark what the 60 is actually represented by, the 60 is actually this distance right here. Because that's the y value, that's the velocity we're traveling at. And in fact, if I continue this geometric figure here, we'll see that we have a rectangle whose base is 30 and whose height is 60. And we've multiplied those. I know if I take a rectangle and multiply the base times the height, I find the area. What we've actually found here is that the displacement is the area of that region. So this area right here is the same as this displacement that we just found down here. That was pretty easy to calculate because of the fact that our velocity was constant. This is a constant velocity right here. The question is, can we do the same thing at any point on this function? And the answer, of course, is going to be yes. But you can see the difficulty that will ensue when it's not a constant velocity. For example, if we look at the interval from 0 to 30 seconds, that again is a 30-second interval. However, I can see that I don't have a nice geometric figure here to find the displacement, but I do know that if I multiply my velocity times my time, that is, if I multiply my x's times my y's there. The x's is the time, and the y is the velocity. Then I also find the area of this region and thus the displacement. The difficulty is the fact that this is a variable velocity. But in either case, the definite integral would tell me the displacement. And it turns out that the definite integral is actually the product then of your x's and y's. And we'll just make a note of that. Product of x and y. Okay? The example we saw there, our x was our time. This was our x. And our velocity was our y. We were multiplying x times y to find displacement, which is that area, that definite integral. So another way to describe a definite integral is a product of x and y. All right, let's take a look at another example here of actually calculating a definite integral using this counting squares technique. So take a look at example 1 there. Example 1 says to estimate the definite integral of an exponential function, f of x is equal to 8 times 0.7 raised to the x from x equals 1 to x equals 7. All right, so let's write down what the function is here. They said f of x is equal to 8 times 0.7 raised to the x, and they're going from x equals 1 to x equals 7. Notice, by the way, that they have to give you some interval here along the x-axis, starting at x equals 1 and ending at x equals 7, so we can calculate the area. They can't just give you one x value, they're going to give you 2. So we have an interval. All right, so the way that we're going to do this, first thing we need is a graph of our function. So I'm going to grab my calculator here and punch in the equation of this function. So in y1, let's put in, it was 8 times 0.7 raised to the x. They even gave us an interval to consider here. They said we're going from x equals 1 to x equals 7. So I'm going to go to my window, and I'm going to set up my window to go from 1 to 7. And I'll leave my x scale as 1 for right now. For the y values, if you're not sure on this function what a decent window would be, they gave you a picture of it in the book, so obviously you can use that to kind of help you out. But if you're not sure, one way you can come up with a decent window for this is to go to your table and set up your table first. So we're going to go to our table setup. I'm going to start out my table at my x min, which was 1. And I'm going to set my change in my table to my x scale. As long as I've set those two with decent numbers there when I set up my window, this will work pretty good here. I'm going to leave these two at auto because it will automatically generate a table for me. Go to your table features, second table, and it will generate some y values for me. So I can see that at x equals 1, y is 5.6, and then at 2 it's 3.92, and so forth. It decreases all the way down to at 7, it's at 0.65. So I can see that the highest this ever gets is 5.6. I'm going to go ahead and set the maximum then for y's. Let me go back to my window, to be 6. But the minimum, because I want to find the area between the x-axis and my function, I always want to include the x-axis. So I'm starting out my y min at 0, even though it didn't quite get down to 0. I want to include that, and I will go up to 6 there. I picked nice numbers here to work with. And I'll leave my scale there as 1 as well. And we can go ahead and graph this. So there is our function. And what I need to do is calculate the area between the curve and the x-axis here. Now I'm going to go ahead and grab a picture of this real quick. So that I can actually do a couple things with this graph. here's our graph of this thing. And just so we're clear on what our objective is in this problem, we are trying to find the area of this region. Here's the x-axis, here's the curve, here's x equals 1, here's x equals 7. We're trying to count up how much area is there. The difficulty that I have here is, of course, it's hard to see where exactly my squares are because I can't quite see, there aren't any squares there to see really, but if I looked at my scale along the x and y axis, I could kind of see some squares to show up. So what I have given you is a program called Graph Paper to help us with that step. So let's try using that. If you go to your program menu and then go to Graph Paper, I'll go ahead and run that program there real quick. And you can see that here is a graph, or a graph of our function, as well as it's placed on graph paper, it looks like, in essence. Now it would be a little bit easier to calculate the number of whole squares and the number of partial squares. So let me grab a picture of that as well. This will definitely be more useful for me in solving this problem, but I just wanted to make sure in that first graph that I grabbed what exactly we are trying to do. And we'll just move this down below here. All right. So here's my graph of this function, and I have squares in there that I can definitely see and count. So the process that we said we have to go through is first we have to count up the number of whole squares. So I'm going to just keep track of these, and you need to do the same thing as you solve these problems for me. Count up the whole squares here. And I'm going to go ahead and just mark these as I go. And I'll start over here in the bottom left corner and just work my way around here. So this is 1, 2, 3, 4, 5, 6, 7. This one right next to it, I can see a little pixel show up in the corner there. So I'm not going to count that as a whole square. If you want to count it as a whole square, that'd be fine. But I'm going to keep that as a partial square. I'll call this one 8, and this will be 9. So I have a total of 9 whole squares. And we have to count up the number of partial squares. And so as I go through and do this, I'm going to just mark down what approximately I'm saying the partial squares are. And again, we're going to try to do that to the nearest tenth. And I'm going to go ahead and write it on my graph here. You probably want to write this on a separate piece of paper as you're doing this, or on your, I shouldn't say a separate piece of paper, but on your paper as you're looking at your calculator screen and doing it. I'll start up here in actually the upper left corner and work my way down. So I'm going to say that this first square here, that looks like it's about 0.2. Again, we're looking at the area of this little chunk right here. That little triangular region is all we're looking at. Okay. Now for the next square, it might be a little bit difficult to kind of calculate there, but if you were to draw a diagonal right through that next square, that would mark half. We're definitely a little bit more than half, so I'd probably say that's close to 0.6. You don't need to go through and do that for every single square, but I'm just trying to help you see what exactly our calculation is that we're trying to make. The next one looks like it's a little bit less than a half, so I'm going to call that 0.4. This one looks like it's very close to a whole square, I'm going to call that 0.9. The next one looks like it's 0.4 or 0.3, I'd probably say it's 0.4. The next one here, again, that was the one that was close to a whole square, but I didn't count it. I'm going to call that 0.9. This next one is 0.7. The next one is 0.1. And the last one down here in the bottom right corner, I'm going to say that's 0.8. Okay? Again, you don't have to spend a lot of time trying to figure out is it 0.8 or 0.9 or 0.7. Pick one of those and go with it. Whatever your first impression is with that square, use it and go on. All right, so let's go through and tally up what we end up with there. I'll start up here in the upper left corner again and just tally these up as we go. So 0.2 plus the 0.6 is 0.8, plus 0.4 is 1.2, and then 2.1, 2.5, 3.4, 4.1, 4.2, 5. So we get a total of 5. Doesn't always end up being a nice number like that when you get done, of course, but that's what we end up with here. So let's tally those up. Number of partial squares plus plus the number of whole squares. When we add those up, we get a total of 14. And then the last step of this process, remember, is to count out the area of one square. And if you go back to your window to help you figure this out, if you recall, we set up our window so that the x scale was 1 unit and the y scale was 1 unit. So that means that the area of each square is 1. 1 times 1 gives us 1. So the area of each square is 1, thus we are going to multiply this by the area per square, for each square there, which is 1. So obviously in this case, forgetting to multiply by 1 wouldn't change our answer, of course, but we definitely want to make sure that we include that every single time. So 14 times 1 gives us 14. So our approximation for the definite integral turns out to be 14, which is actually very, very close to the exact answer. Okay. Let's try that one more for one more example. Example 2. On the next page says you have a graph of the velocity function. V of t is equal to, go ahead and write this down. V of t is equal to negative 100 t squared plus 90t plus 14. Where t is in seconds, v is in feet per second. Estimate the definite integral with respect to t from 0.1 to 1. T equals 0.1 to t equals 1. Okay? So let's take our calculator here first of all and punch in that equation, and then we'll get a window set up here. So we have negative 100x squared plus 90x plus 14. And for a window, they said to go from 0.1 to 1. Notice I'm going to use the same domain that they've specified in the problem. I want my graph to completely fill that window. It's really important in this process that you get a very good picture of this function so that your counting squares technique will be as accurate as possible. So I'm not going to go from 0 to 1 or 0 to 2. I'm going to go exactly from 0.1 to 1 like they said. And I'm going to change my scale. Your graph paper function is based on drawing that grid line in there based on your scale. So I'm going to change my scale here. I think we'll change it to 0.1. Now for the y's, again, if you aren't sure exactly what to do, let me show you how you can use your table again to help you out. Started out at 0.1, our x min. Have the table change by 0.1, our x scale. And then go to your table, second table, and look at the y values that you get here. It starts at 22 and then increases up to 34, and then starts decreasing back down to 14, or actually 4 at x equals 1. Okay? So we can use that to help us set up a pretty decent window of this thing. It looks like probably if I let this thing go up to probably 34, it probably is going to go a little higher than 34 actually, so I'm going to set my window to go from 0 to 35. We'll see if that's large enough. And I want to equally divide this window up, so I'm going to set my scale to 5 here in this case. And I'll graph that and see what we end up with. And if it doesn't show up on your screen, or if it doesn't quite show up with a nice graph there, you definitely want to resketch this thing or change your window is what you want to do, and then resketch this thing. But again, I want my graph to go all the way from the x-axis at the bottom of my screen, and I want the graph to go all the way to the top. And then I only want to go from left to right on the domain they specify. That's what I have here. I got a pretty good sketch of this thing. So let's have it run our graph paper program. And let me grab a picture of that. All right, so we got a nice little sketch of this thing. We should be able to go through this same process that we just went through on the last example. So the first thing we do is count up the number of whole squares. I'm not going to worry about numbering these as I go, but I am going to mark them. By the way, as you look at your graph here, this is actually a pretty nice number of squares here. You don't want to have too few squares, and you don't want to have too many. If you have too few, then your approximation is not going to be very good. If you have too many, then you aren't going to be able to see your squares very well. It's going to be a lot of counting. So I would say that if you're in the range from like 30 to 50 squares, you're in the right range here. Which if you look at ours, we have 9 squares along the bottom, and we have a total of 7 squares vertically. 9 times 7, that's 63 squares. We're a little on the upper end, so I could back off a little bit, but that's not a bad picture that we've got here. I'm going to stick with this and go with it. So let's count up our whole squares. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39. It looks like we have 39 full squares. Again, depending on your window and your scale that you set up, you might have a slightly different calculation for whole squares there because of the fact that you either have more squares on your screen or fewer squares on your screen. The next thing is to count out the number of partial squares. So the number of partial squares, I'm going to approximate these, of course. I'm going to say that this is approximately I'm going to start on the left here, 0.8. I'm going to say that's 0.2. And then 0.9, and 0.2, and 0.6. So that's 0.9. Looks like there's actually some symmetry here in my graph, so I'm going to say that's 0.6, 0.2, 0.9, 0.2, 0.8. So that's 0.1, 0.6. That one was almost a whole square here right below, but that's 0.9 for me. 0.2, and finally, so that's 0.8. Okay? Let's go through and tally those up. So we have 0.8 plus the 0.2, starting on the left here, is 1, 1.9, 2.1, 2.7, 3.6, 4.2, 4.4, 5.3, 5.5, 6.3, 6.4, 7.0, 7.9, 8.1, and 8.9. Double check those calculations there and make sure that's right. As long as that's right, we should have 8.9 plus the 39, which would give us 47.9 squares. And again, the next step is then to multiply by the area per square. So the area per square, now again, if you go to your scale on this thing, you'll see that you set the x scale to 0.1. This is 0.1. And you set the y scale to 7. Or excuse me, it was 5. Double check your graph there, but we set that to 5. So 5 times 0.1 gives us an area per square of 0.5. Multiply by the area per square, 47.9 times 0.5 is going to give us 23.95. And that is our approximation there for the area of that region. Okay? And that's, again, a very close approximation. Now, the one last thing that we should add in there is the units. They told us that the velocity was measured in feet per second and that our time was measured in seconds. So this is feet per second along this axis, the y-axis, this is in seconds here. And again, since we're finding area, the product of x and y, we can multiply those two to get the units. In other words, it's feet per second times seconds. So the seconds cancel out here, of course, and we're left with just feet. So we get 23.95 feet. That's our approximation for the decimal. And that's the end of this section.